Okay, so our unit 5 test review. It says find the inverse of 3x squared plus 2. So remember, when you're finding the inverse of something, it's been a little while since we've done that. You zoom on it a minute and then it'll clear out. The first thing you do is you say y equals that 3x squared plus 2. And then the second thing that we're going to do is change our x and y spots. So we have x equals 3y squared plus 2. Let's just blot out the 3 just to make it a little bit easier. I just don't really like this one to review for what it is. We're just gonna change it a little bit. There we go. Okay, so then remember, once we've changed our x and y spots, we want to isolate our y. So what I would do is subtract 2 from both sides. So we would have maybe x minus 2 equals y squared. And then from here, we're going to take the square root of y squared because we want to know what y is, not y squared. I'm just going to kind of mirror it and say y equals the square root of x minus 2. Which really, if we write that inverse notation, that would be f to the negative 1 of x equals the square root of negative 2. It doesn't say it, but you should say any restrictions. Just to go over that for just a minute in case you have one like that on WebAssign. State restrictions. Remember, we don't want a negative number. So it's like you could say x minus 2 needs to be something greater than or equal to 0. So x has to be a number greater than or equal to a positive 2, right? You plug 2 in there, that's what would zero that out. So that would be the only restriction, is x has to be some number greater than or equal to 2. But this right here is the actual inverse function. Number 2, sketch a graph. This just has y equals to x minus 1 power. You can use anything you want for x. I probably wouldn't use really big numbers. Since it's just x minus 1, it's probably not going to be too bad of a number either way. So I might just still use my negative 2, negative 1, 0, 1, 2. You may just want to use 1, 1. You may just want to use 0, 1, 2. It's really up to you what you use. I don't care. So remember, you're just plugging that in and simplifying that. So that's like saying negative 2 minus 1, which would be 2 to the negative 3rd, which is 1 over 8. You'll plug that into your calculator and it will do all of that for you. You know, in WebAssign, you'll just probably be picking the appropriate graph, but you need to know what points to kind of look for and check for to pick the right graph. So this would be like 1/4. This would be like 2 to the negative 1 is 1/2. 1 minus 1 is 2 to the 0 power. So remember, that's like 1. 2 minus 1 is 2 to the 1st power. So that's 2. You may want like a bigger number since all these are little fractions. You don't have to. I'm just doing it for myself. Like if I were doing this, I probably would want to see, I don't remember, 3. 2 to the 2nd power is 4. I would probably want to see a couple of full numbers rather than all these fractions. But you really only have to do 5, or at least look for about 5 of them, because you're going to be picking the appropriate graph, right? So negative 2, negative 1/8 would be kind of like right here. They're all going to be really close to each other. Negative 1, 1/4 looks about the same because it's such a small graph. 0, 1/2, you kind of start to see a little bit of a dip finally. 1, 1, 2, 2, and 3, 4. So you get to see a little bit more of it happening. So just using a T-chart, hope you guys kind of remember that. Log, if I were to graph this, remember we need to turn that into an exponential statement first. So 3.
So your graph be the other way, going up and down. Yeah.
What did I do?
A is negative.
I did. Why did I do that? I don't know. I like totally. Why did I say negative? Who knows? Let's redo it. But my -2 1/8 would be here. Yeah, I like totally flipped it, didn't I? Entirely. 1 1 2 2. I'm sorry, guys. 3 4. Yeah, so the graph in red is correct. The other one, I don't even know what's happening in my brain. Nothing that was correct was happening in my brain. Oops. Okay. I wondered why you guys are kind of like, what's happening here? Thought maybe something's going on. We have to turn this into exponential. So this would be like saying 3 to the y power equals x plus 1. And then since you have an exponent in the y, what would be best is to isolate our x, but then choose values for y. That makes sense. I guess you could keep it like this and you could choose values and then go find your x. It would just be a lot of work. I would still isolate the x. So 3 to the y power minus 1 equals x. But in this one, we're choosing values for y so we can find our x. So we didn't choose. So this one we chose our x values. When you're doing your log statement, a lot of times you're going to be choosing your y values because that's what's up in the exponent. A lot easier to work with. And you can choose really whatever you want, -2, -1, 0, 1, 2. I wouldn't choose big numbers because think about like 3 to the 5th power or something would be a really big number and you don't have enough space on your graph to do that. That would be like the only thing I would think about with why you might choose some numbers over another. So if I take 3 to the -2 minus 1, remember that would be like saying 1/9 minus 1, or just plug it into your calculator, 3 to the -2 power, and then arrow over because you're subtracting that. Subtracting 1 from that, so it'd be a -8/9. And then 3 to the -1 minus 1. So we're plugging in our y's to find our x. It'll be a -2/3. 3 to the 0 power minus 1. So that's like saying 1 minus 1, which is 0. 3 to the 1st power minus 1 is 2. And 3 to the 2nd power minus 1 is 8. Let's see if I can graph these right. Let's go over to x, which would be like -8/9. So we're going really close to -1 down 2. -2/3. So we go over, not quite as far, but it doesn't look a whole lot different. It's just somewhere between. 0, 0 is here, so we start to see it to turn. 2, 1 is here, and 8. 1, 2, 3, 4, 5, 6, 7, 8. I don't know if I counted right. My eyes messed up. 1, 2, 3, 4, 5, 6, 7, 8, 2. There we go. Okay, the next one, you're just using a calculator to solve this and making sure you round to the appropriate place value nearest thousandth. So we're typing in 10 to the e second natural log 4 times the square root of 5, arrow out from underneath that, minus pi. So it looks really busy, but you're just telling your calculator to do all of that. That's not the fourth root. That's the only thing I would draw attention to. That's in front of the radical. It says error overflow. So maybe you can't do that. I used to not do this one with you guys, but I can't remember why. I think because of that radical and that pi up there. I don't think it's possible. Oh, I did it that time. I don't know what I did wrong. Who knows? But I used to not solve this one for some reason. Maybe because I didn't put it in your test. You may have one like this on the website test. Tenth, hundredths, thousandths. What did we say? The nearest thousandths. The next digit was a 0, so obviously we would keep 7 the same, and that would be our answer. Number 5, solve each equation by using properties and definitions of logs and exponentials. Obviously, the instructions on WebAssign are going to be a little bit different. It's going to look a lot more like your homework. One thing you could do is, what just I thought of is maybe go back and open up your old assignments and print them. That would be really helpful when you go through your test, I think. Then you can like see the topic that went with it. And the instructions will be the same verbiage. Okay. But here, is there anything that we can raise 3 to get 11? No, so this is our change of base where we say log 11 over log 3, or if you like to see it in exponent or in log form, which we should be in the habit of doing anyways, that helps us set that up. Remember, if it says the exact answer, which one of them, I know it does say the exact answer, and then one says like the nearest hundredth or something. So if this is if it says give the exact answer, that's what you would answer. And if it says maybe around to the nearest thousandth, just because of what we saw above, then we would actually calculate it. Log 11 over log 3 would be, rounding correctly, would be 2.183. Because the digit to the right of that 2 is greater than 5. But if you happen to round wrong, you're submitting that shown work. That's the whole purpose of that. So I can look at it. What do you think we're going to do on 6?
We multiply both sides by natural log.
Yeah. Because you see that E, that looks different. I don't have my, oh, I do my okay. Because we have E, if I want to bring that 4x down, we're going to multiply both sides times natural log. And so that brings us out of the exponent world down in front of 4x, and natural log times E is 1. So it's kind of like it cancels, equals 184.125. And then all you would do is finish solving for x by dividing by 4. So 184.125 divided by 4 is, let's just write all of that since it did end. I won't even round that one. If you weren't given instructions, you wouldn't either. You just write it all. Practicing writing something as a single log. Always a good thing to do. Remember, there's not an equal sign, so there's nothing to go solve like we have down here that we've done more recently. We just write it as a single log. Remember, this means these two things are getting multiplied, and this right here means that it's going to be in the bottom part of a fraction, right? Because of the minus sign. Before I start doing that, though, we do have some exponents. So you can kind of think this is like saying to the 1/2 power. This is like saying to the 3rd power. And this is like saying to the 4th power. Remember that? But what would 1/2 power really be? You can't leave it as 1/2 power.
-2.
So you're on the right track thinking about bases. Think about radicals now. The square root. Yeah. I know, it's like weird stuff, really. So we would say we're taking the square root of that x minus 8. Kind of a weird one. And I would put that in parentheses times x plus 5 to the third. If you had one like that on WebAssign and you did just put x minus 8 to the 1/2 power, I'm probably going to give you all your points back. But you know, just remember 1/2 power makes a radical in this case. If we were trying to make a base of 2, we could say 2 to like the negative first power. Good. And then over x plus 3 to the 4th. But this one, we actually have to go solve. So we need to, if this is log 2, that can actually be simplified, couldn't it? Yeah, but I think we have to condense it, so never mind. I don't know what else. I was going somewhere else. So let's go ahead and write our condensed log forms first. So we're saying log 2 times x equals log 3 times x minus 1. So see how my brain was working? I like saw log 2 and I thought I need to simplify that. Oh wait, I don't, because I know I'm solving an equation and I need to just condense it. So hopefully kind of work through those things that kind of tells you why we do it sometimes and we don't. Remember those equality statements of logs. If it's log on both sides, we can cancel, then we can just go start solving. So 2x equals, and we can distribute 3x minus 3. You can move whatever over. Since I only have a variable on both sides and a constant only on one, I'm still going to move this over here. It just means that I would have to divide or change their signs in the end as a second step. But remember, we do need to go back in and make sure that would be a real answer. Remember to check it. Sometimes I forget, but like plugging that in, that's still a positive. If x was 3, it's positive, and 3 minus 1 is positive, so it does check out. If we were to put this in exponential form, we know that there's no number. 22 to a number could never equal 5, so we know that that's change of base as well. We already did one like it, so we're going to say log 5 over log 22. Again, if it was the exact, this would be your exact answer. If we say round, we would go actually type it in and solve. So log 5 over log 22 would be maybe 0.521 if I rounded to the nearest thousandth. Any questions? You guys kind of remember this stuff? I mean, you did the hardest part, really, in the last assignment that you're doing. This is when we start working with those negative exponents again, because we had a problem very similar, but not exactly like this in our notes. This would be like saying 3 to the 1/2 power because it's a radical, but then that's being raised to the 4x plus 12. So remember when we were solving these, that exponential equality theorem, you know, if my base here is 3, we're hoping that 243 can be broken down to represent 3 to some number. If you don't remember it, that's when your factor tree is your friend. So 3 times 81. And then we have some 3s. So you're just breaking it down to the prime factors where you can't break it down any further. So 243 is like saying 3 to the 5th power because there's 5 3s. So if I were to put that down here, though, that's not up in the top like a positive number. Remember, this is still, sometimes I forget to write that part. But to make that a negative number, we can pull it up to the top. I mean, to make it a whole number, we make it a negative exponent. So it'd be like saying 3 to the negative 5th times that x plus 10. Because we want like bases, so we can kind of manipulate that. And then just come over here and work with the exponents. So 1/2 times 4x plus 12 equals -5 times x plus 10. So then we would just distribute and solve for our x. So 1/2 times 4 is 2x. 1/2 times 12 is a positive 6. -5 times x is a -5x, and a -5 times 10 is a -50. So you can move your x's or your constants first. I'm going to move my x's to the left and call that 7x. And then move this over to the right and call that -56. When I divide by 7, x is okay. Not too hard, right? The only thing is being able to kind of think about those fractions and those radical things. I would maybe put a star by that because that's where you're kind of reviewing both of those rules about exponents, radicals, and then those negative exponents. Number 11. If we're solving that one, I see that I only have log 1 time. So if I put it in exponential form and then solve for x, I'll be good. So if we take 5 to the 3rd power, that's 125. So you need to simplify that before you do anything. And so since the term that has x is right here, I would start by subtracting 29 from that first. So that would be a 96 equals 12x. And then divide by 12. So x equals 8. Number 12. So on this one, 3 was already like a prime number. We really cannot turn 32 into being like 8 to some power, right? Because we know 8 squared is 64. It's already bigger than 32. But can we turn 8 into like exponential form? Yeah, like if you think about your factor tree, if I take 2 times 4, that's 8, and 2 times 2 for 4 is 8. So if we turn 8 itself into exponential form, that'd be like saying 2 to the 3rd power, and then it had an x. 32. Actually, I could probably just up here, but like 32, if I take 2 times 16, 4 times 4, and some 2s, you might have thought of other factors, but 32, if I take 2 to the 5th power, that's going to be 32. I went ahead and just wrote it to the right because of space. But if I want that to be a whole number like I have here, then I need to say 2 to the negative 5th power to bring it up to the top part of the fraction. So sometimes you do need to factor both sides to be sure they have the same base, and we can do that on this one. So they do have the same base, so really we're just saying 3x equals -5. So x is an ugly fraction, but that's okay. So x is a -5 over 3. Make sure you have your formulas handy because you will have some questions that you use those continuous formulas or the compounding daily formulas. Number 13 says, how long would it take for $1,000 to double if it was invested at, I think that says 3.8%, or is that 5? Is it 5? It's 3.5%. Yes. Okay, I wrote over it. Compounded continuously. So I know my principal means that's how much I'm gonna invest is 1,000, but then they say that it doubles. Remember, that would be like your ending balance. So that would be $2,000. So 1,000 times 2. My rate we said was 3.5%. So we need to turn that into decimal form, which would be 0.035. It wants to know how long will it take for that to become 2,000. So remember, we're using our A equals P times E to the RT power. So remember, A is like your balance at the end, and that's why we said A equals 2,000. So our principal was 1,000 E, our rate was 0.035, but we don't know T. So since our unknown, it's a little bit confusing because you see E and you think that's a variable, but it's not. That's actually something, but our unknown is right here with this term. So first, let's get E by itself. Let's divide by 1,000. And since that does divide evenly, I would go ahead and just say 2 equals E to the 0.035T. We did one kind of like it earlier. How do I bring T down? Multiply by natural log. Yes, multiply by natural log. Write that over here. So we have the natural log of 2. If you want to put it in a parentheses like you'd see in your calculator, you can. But then we would bring this down, which was a point. I kind of wrote over my point, 35T. And my natural log and E, when they multiply by each other, equal 1. So it's like they cancel out. So to get T by itself, we're just dividing by 0.035. So natural log is just in the top part of your fraction. Or if you type divided by, that's also okay. But natural log of 2 divided by 0.035. They would give you rounding instructions, but a lot of times when they talk about how long year, they might round to the nearest year, like we did in our notes. So just read your rounding instructions. But if this was 19.A, then we would say 20 years. I said A, 19.8, then we would just round and say about 20 years. $14 is basically just giving you the values to plug straight into that. Make sure you review. In the review, it looks like I didn't give you one of the compounding interest formula. Like maybe it compounded. Let's change it so that we do one like that. Let's say it compounds monthly. I don't know. Just so that we have to use that other formula, at least in reviews. I know we just did this, but P times 1 plus our N, or not N, our R over N raised to the NT power. So in this case, my principal is going to be $100. My interest rate, we said, was 7.5%, which we're going to turn into 0.075. And our time is going to be 25 years. The only other thing is the verbiage, it compounds monthly. That means N equals 12. So that's how we know that we use this formula rather than this one. If it said compounded continuously like it did before, we wouldn't use this formula. We would just use those values they gave us and we would plug it in here and solve. Okay, So we have A equals 100 times 1 plus our rate of 0.075 over, it's going to compound monthly, raised to the 12 times 25 power. So we just plug it in our calculator. 100 times 1 plus 0.075 over 12, close your parentheses, raised to the 12 times 25. So since it's money, a lot of times we just round to the nearest cent, but read the instructions. So 648.29. So remember, compounding interest is kind of like a snowball. The more money you have in it, the more interest it's going to make each time it compounds, which will make it the new balance until it compounds again and again and again, and it just grows a lot faster. Smaller amounts of money, it doesn't really seem like it affected that much, but I mean, it did make some money, but that's for a long time, 25 years. And then the last one, this was your carbon dating problem. This formula we worked with a lot is in your notes. That's just the formula, but it says a bone is found to have 22%. So remember, that's going to be our 0.22. Your P of T value equals, and then we have everything here the same, 0.5 to the T over 5730. This is like a fraction that I like to use as a forward slash because it just kind of helps me separate it like it's a term for now. We want to know how old is the bone, meaning we're finding T. So this is the only thing over here with T. We're like up here, it had the 1000 in front of the E. That's why we did something first. But this one doesn't have anything. So if we can just jump right to multiplying both sides times natural log. Then we can pull this down in front of it. So we have the natural log of 0.22 equals the natural, or not natural log, I didn't need to write that yet, equals them pulling this down in front, T over 5730 times the natural log of 0.5. Technically, you could have written that first and just said times T over that, but we're used to pulling our exponent in front, so I just try to stay consistent. And I do this fraction like this because it helps me see if I'm trying to isolate T, then that means this is the entire term that I'm trying to get by itself first. So if I divide by the natural log of 0.5 to make that cancel out, then I have to divide by the natural log of 0.5 over here as well. So the natural logs don't cancel. Remember, you can put in your calculator natural log of 0.22 and you get an actual number. So don't do that if you're tempted to. I'll go ahead and rewrite this like I do so you can see what's happening. May kind of get to where you know what's happening and you don't, but this is like saying T over 5730, which means you have to multiply times that 5730. So you're taking all of this times 5730 in your calculator. So let's do it. And then we're done. 5730 times, give me a second, the natural log of 0.22, the natural log of 0.5. Hopefully you've kind of picked up on the pattern. Whatever the percentage is, I'm kind of lazy and I always do. This is always the only thing that's different when you're figuring it. And then this one often says round to the nearest year as well. So if it was 12,516.7 years old, then that means it's 12,005. Actually, I think this one's 100 years, isn't it? I think so.
That's what it was.
Yeah, let's do it like that. This one's 100 years. So let's say we round to the nearest 100. And I think it is on the test too. I think I looked. So this would be 500. Pretty old. Pretty old. Okay, so that was the test review for our unit 5. I recommend you kind of looking over that. I will say the review